All right, hello everyone. My name is Campbell Ong, and I am a Dragonfly testbed software and flight software developer at the Johns Hopkins University Applied Physics Lab. And I'm here to talk to you today about testbed software, what it is, and how it is critical to flight software's early testing and integration with flight hardware. All right, so we got some context yesterday from a few talks, but for those of you who are not aware, Dragonfly is a mission of astrobiological discovery set to launch in 2028. A Dragonfly rotorcraft lander, pictured there on the right, will explore a variety of locations on Saturn's moon, Titan. It's carrying with it a large suite of instruments to study the prebiotic chemistry of the atmosphere and surface. You can see the list there on the right. And the science that's done there is going to push forward our understanding of the building blocks of life, including how life may have developed here on Earth. So part of this mission is it has to fly. A critical aspect to flight is closed loop rotor control. So the Dragonfly flight software must be able to autonomously control the 8 lander rotors. Flight software contains mobility, guidance, navigation, and control, or MGNC, auto-generated algorithms, which are written and delivered by the mobility team. One of these algorithms has to do with the rotor drive control. Flight software's data path to the rotors is through an avionics board, an avionics board connected to the rotor drive electronics, or RDEs, that manage the power flow to the rotor motors. And as with any mission or technology, you want to do baby steps towards your eventual goal. So the flight software and mobility team and overall mission wanted to do a demonstration of just a first rotor spin of a single rotor. So this is a highly simplified context diagram, but in general, it gets the picture. So as mentioned, we have flight software containing those MGNC algorithms running on the SBC, or single board computer, and it is connected to that avionics slice called the navigation coprocessor, or NCP. The NCP then has UARTs connected to the rotor drive electronics, which contain those electronic speed controllers that then control the rotor speeds. So a big question is, how can flight software and mobility teams test a rotor spin prior to Titan and even prior to any lander integration here on the ground? Part of the answer is that testbed software communicates with a real NCP and then emulates the missing RDE and rotor pieces. So it looks like this. I don't expect you all to read through all this. I'm going to be stepping through basically all the little pieces of this throughout the talk. But this is, especially the right side, is pretty much what a bunch of teams, everyone who's involved in this, mobility, flight software, avionics, testbed software, like everyone came together to really draw out the data flow of what is necessary to get this done. And it's obviously a lot. The left side is largely abstracted too. But and I can't even talk to everything on here. The yellow lines more flowing along the bottom are about timing, and I won't be able to touch on that today. But this is all to show that it takes a ton of effort to fill in the gaps for something as simple as the first rotor spin demonstration. It takes a team. And so at the lab, we designate a specific team called the test environments team. So for Dragonfly, the test environments team is responsible for designing and delivering hardware, software environments necessary for the development, testing, and verification of the flight system, which of course includes flight software. There's 5 distinct types of test environments: instrument development, hardware checkout, flight software development, which I'm focusing on today, integration and test, and then mission ops. As you can see on the right, testbed software is a level 4 subsystem to the test environments team. With the exception of the instrument development test environments, the core of each test environment is the test bed. So what is a test bed? Test bed is a combination of custom hardware and software that is largely made to fit each mission. It includes the test avionics, test interfaces, data analyzers, a computing platform, and power supplies. And computing platform is highlighted there because that is where the testbed software runs. So testbed software is a collection of applications and libraries that perform a variety of functions, but including it emulates spacecraft hardware, injects air conditions for fault testing, generates test data sets for the testing of interfaces, and supports closed loop simulations. They run within a custom pub sub framework and are written primarily in C++, though our team uses a variety of other tools, some of which are shown there. And then my colleague Gina kind of touched on this yesterday, but it also runs on a virtual platform, or RSIL, software in the loop. But I will not be talking about that today because I, again, do not have enough time. So today we're talking about a very specific use case, that involves the avionics, mobility, and CNDH primarily. But testbed software design is driven by pretty much all of the subsystems. All of the ones listed here, we have to interface with, whether indirectly, but a lot of them directly as well, which means we touch pretty much everything and have to understand a lot, hence me talking about glue. But testbed software's design is customized to fit each user's needs and really get to the bottom of what do you need to have confidence in your system and how your system talks to another subsystem. And something that I really feel passionately about that I also don't get to fully touch on is the fact that I think it's super cool that testbed software spans all of the mission phases from the lower level instrument hardware, flight software, up to INT, up to MOPS. And in order to do that, we have a very modular design so that we can add pieces, and then once the hardware is available, we can take it away, and modularity makes this possible. So in addition to supporting the test as you fly mentality, such as the spacecraft and environment emulations, testbed software also provides a lot of non-flight test features, some of which are, for example, via a test port, we provide telemetry in addition to or in lieu of spacecraft telemetry sent via the radio. We also enable fast MRAM loads of flight software images. We also have faster than flight uplink and downlink. All of these things really help reduce test setup time and teardown for our users, including flight software users. For example, quick retrieval of SSR data post-test so that they can get to their analysis. And so, as I mentioned, like any mission, testbed software is similar to flight software in that there is some heritage code, but we also have a lot of custom things that have to come up for every mission. But in general, from mission to mission, we have the same set of 4 categories, I guess, of our applications. The first of which is utility applications. These provide any additional necessary test functionality that's not covered by the 3 I'm about to mention later. But for example, we have our memory manager, which, as I mentioned, allows that fast load of flight software images. We've been The flight software developers have reported to us that on average, it's reduced their load time from 6 minutes down to 4 seconds. Additionally, we have our test pattern generator application. This generates and validates test patterns for verification of avionics interfaces, such as UARTs or SpaceWire links. Lastly, one that's related to our first rotor spin demo that I'm talking about today is what we call our single board computer application, but it is a utility application in that it reads and telemeters registers or memory areas of interest so that the hardware and software developers can see into what's happening, unlike they might normally would in operations. So we see, I have a graph there on the right. So this is one little piece of that giant graph that I showed you earlier. But we have our SBC application is polling that navigation coprocessor registers that are of interest while we're running the simulation and sending it down to ground. Next, we have our interface applications. These provide connectivity to external components, whether it be ground software, hardware emulators, sensor stimulators, or avionics interface cards. For our first rotor spin, we had a few of these involved. We had our NCP interface that essentially talked to rotor drive electronics, which I'll explain later, getting the command and telemetry UART information, into the NCP slice and off to flight software and avionics via this electrical ground support equipment, which I have some pictures of those cards there. When we also have on the right, you can see our what we call our mock apps. Those are essentially just both the spacecraft or flight software's interface to the ground, so spacecraft commanding and telemetry. And then on the right side of that, you can see our testbed software commands and telemetry as well. And then at the bottom of that, you can see SpaceWire interface. So that's where we have our interface to the SpaceWire cards that are then connected to the avionics and flight software. So I had mentioned earlier that I'm focused on the flight software development test environment, but this is an example of the hardware checkout test environment specifically for that NCP board that we were talking about. Uh, Within the hardware checkout test environment, Testbed software enables the avionics team to test and verify necessary board capabilities and interfaces in advance of flight software integration. So that once we get to this first rotor spin, that doesn't have to be a variable that's in question. So you can see on the left picture, the NCP is there on the right, connected to that test fixture. And on the left, you can see those electrical ground support equipment or first circuit cards. And on the top, you can see it says Ethernet interfaces to testbed software. So testbed software then has a connection out. And then on the right picture, you can see our testbed. And there's our computing platform, which testbed software runs on. Next, we have our model applications. These provide the underlying behavior for our emulation applications, which I'll talk about last. These essentially are just Simulink wrappers encapsulating truth models, such as sensor data or sensors, spacecraft dynamics, body dynamics, and actuators. These essentially supply inputs to the flight algorithms within flight software. And I had mentioned before that the mobility team is who writes and generates those auto-generated algorithms that are running within flight software. Similarly, that same exact team delivers to the testbed software team a mobility truth model, which you can see on the diagram. It contains the rotor motor and RDE models that we need. And so that is our mobility truth model wrapper application. It generally includes the environment and lander dynamics and EPS models. And as you can see, those bottom two bullets include the rotor and RDEs. And then I should mention, if you look at the graph, you can see that we're able to load parameters to this truth model, as well as get general truth model information out that the testers would like to see to understand the status of the truth model. And then you can see our RDE emulation, which I'll talk about next, is going to be flowing data from the avionics and flight software, specifically RDE commands from the MGNC algorithm into the RDE, into the mobility truth model wrapper, into the truth model, which then calculates what the correct RDE output would be in flight and out back to the avionics and flight software. So that leads to our final category, the emulation applications. These emulate the data interface of spacecraft components. They process the outputs from and supply inputs to flight software. For example, we have our radio emulation. So we don't have a hardware radio yet, but we're able to use this emulation such that we can still send the true spacecraft commands to the flight software as well as receive telemetry via SpaceWire. And then on the right, you can see we have, as mentioned, our RDE emulation, which again is that sort of pass-through emulation for supplying the mobility truth model data to and from the flight software. So this leads to our first rotor spin demo. Again, a very large chart, apologies, but this is a ground software display that one of the flight software developers put together specifically for this first rotor spin. So I think it still speaks to the fact that there's a lot of teams working on this together, and it's a lot of information and things to track. But the way that our process works, I think we're able to really narrow down such that we know where to look, like what we're testing is flight software at this point for this demo. And I'll try to explain a little bit of it. Don't get too caught up in the details. But on the left, we see information regarding that MGNC autocode and some graphs. But on the top, you'll see, I should mention in green is the flight software telemetry. And then in the red is all the testbed software telemetry. And along the top is basically the flow of those RDE commands coming out of the MGNC algorithm out through the hardware into testbed software. And then on the right side, that big column is our mobility truth model wrapper. And so it takes that input data, creates the correct rotor speed output, and it flows all the way back to flight software. Let's see if I can play this. So this is a clip from the true first rotor spin demo. And you essentially will see that MGNC comes up green and it's put into the correct mode. And then on the right, you'll see that the rotor speed starts stepping up as was set for the simulation. And it'll essentially, it keeps going, it speeds up. And then we have our spinning at the top, in case you can't tell from all this data. And it hits this set point and then the rotors stop. And so it performed as expected. So in summary, test early, test often, and test as you fly, and the testbed software is a huge part of making this happen. Testbed capabilities are needed at varying capacities at every phase of the mission, from avionics hardware checkout to mission scenario runs and operations. For the flight software team specifically, though, testbed software is that glue that enables testing long before spacecraft assembly, synchronous flight software development and testing of spacecraft control systems in a closed loop simulation, and seamless piecemeal integration with spacecraft hardware as it becomes available. Thank you.
Hi, great talk. I have a question about your test pattern generator you spoke to kind of towards the beginning. Following up on yesterday's data coverage talk, how did you generate the data? Was it like known good values? Was it just totally random?
So at this point, so that test pattern generator, I think I had mentioned, is used specifically for the avionics hardware checkout. And at that point, we're not using any emulated data. What they want to know is what they write to the hardware slice. Is that what comes back out? So we just have a general pattern, whether it's like incrementing pattern or fixed pattern, and it's basically allows users from the ground to configure what rate is that at, how many packets, which type do you want. And then it validates the standard protocol that they have for those interfaces. And yeah, thank you.
We can take one more question here.
Got one over here.
Hey, thanks for the talk. Got a stack question. You mentioned having a custom pub sub setup. Can you speak a little bit to why custom, and also, are you going to make yours available open source or something?
Second question, as far as I know, not that I'm aware of. For the first question, I would say I know the developer. I don't know how much I can talk to it. I should try to convince him to come to this workshop one year. But it's partly custom because of the requirements for the amount of data pass through. I know he needed to meet the timing requirements for certain things, and so he wrote it to basically run even faster than what we needed so that we can meet the system's demands.
So such as a mission like this is a very scientific mission. How much redundancy do we have on a mission like this? And the second part is like, you formally qualify it, based on the requirements. And then how much do you go further to run any stressful cases and stuff like that as a kind of validation?
For the first question, again, I'm not sure how much I can say, but yeah, there is redundancy in the system. I would reach out to Zibby Turtle, the PI for these questions, if that's okay. But yeah, sorry. Your second question, I'm trying to remember, was about testing rigor.
Many contractors that I have worked in the past, they kind of pretty much stop on verifying all the requirements. They don't go further to test out the edge cases or the stressful, test case scenarios. So do you do a lot of validation and stressful cases?
Yes, I would say so. From my personal job, I work directly more with avionics on that hardware checkout level is what most of my history is. And I know that, for example, we have like the set high data rate, right? But they like to push those tests past what the system might expect. So, but it really is not up to testbed software what tests are run. That's one of the things that I think is really unique about our team is that we will do whatever you want us to do. And a lot of times they'll ask us as if we're the testing team, like, what should we do? And I'm like, no, you're this system. Like, you tell us what you need to do and we'll make it happen. But I'm aware of some subsystems already, yeah, they stress test things and I'm sure it's system wide.
There was one more question here.
Follow the stack, the custom stack. There are some commercially available pieces of hardware like DSpace that's very expensive and SpeedGoat that's performance versions of DSpace that allow you to simulate real-time systems on relatively, let's say, one-click button auto-generate code for your plant, controllers, and so on. Have you looked into those? And if you did, why have you chosen the custom, your own rack development for a testbed? Over.
I don't know how much I'm limited in experience in being able to answer this question, but just from what I know, like I said, there's a lot of heritage between missions, not just flight software, but paired with testbed software. Like the heritage testbed software has been used with this heritage flight software as well. There's always that question of where do we tear down and restart, bring in something new. But yeah, I personally, I'm not aware of us looking into those, the technology that you had mentioned, but I think I'm missing a part of your question, but I hope that answers it. Maybe we can talk more offline. Thank you.
All right, that's it. Give it up for Campbell.